Hi everyone, in this video I'd like to introduce the proof of the Euler method, namely why the Euler method approximates the real solution nicely. So proof of the statement we want to prove here is a slightly simplified version, but so let me list down some of the assumptions of this situation. The first one is we assume this first order differential equation with this initial condition has a unique solution. This is a consequence of existence and uniqueness theorem. So even in the part 2, this will not be proved. It's going to be a separate video that we prove the existence of a solution of this differential equation with this initial equation. But what we assume, which makes this proof as a little simplified version, is the second condition. So context of this problem is a little bit complicated, but once you read through, it's not that difficult to understand. First of all, we simplify so that our initial point position is 0, and we want to estimate the value of this y at this value beta, which is given. And this is where we start, y equals y0, and this blue curve is supposed to be the real solution. And remember, we only know the existence and the unique solution of this differential equation, but we do not know what this is. And throughout this argument, we play a lot with the existence of certain properties of y of x without knowing what y of x really is. So this type of a proof in mathematics is called ineffective proof. We only know it exists, but we have no idea how big that is and what kind of number it is. We only know the existence of a number, and this argument rely on that existence to show that Euler's method is valid. So I already explained what this 0 and beta is a part of the setup, and there is this unknown function for existence of which we know. So I have to explain what kind of height we're putting in here. This is the width of this rectangle. I have to explain the height of this rectangle. But this y equals y0 is indeed the central position. That's exactly the center of these two positions there. So what is this top and bottom? Main goal is that we're going to put this around, same amount up and bottom, such that graph of y of x is contained in this rectangular box. Don't make it too tight, just make it a little bit wider so that is enough width that we have here, or height of this rectangle, such that this entire graph is contained in here. We can certainly do that. This is an ineffective part. Once you understand there exists this solution, and by extreme value theorem, you know there's highest and lowest point, and which is only the existence. We don't know what the function is, we don't know what the maximum minimum value of this function is, but we know it exists. Therefore, we can certainly put around wide enough such that this entire graph is contained. So choose R that's wide enough to above and below. It's wide enough such that it contains both maximum and minimum around the central point y equals y0. Although the picture indicates that it's kind of the same point here, it's not necessarily so. We just start here and we don't know where it goes, but it is in between these two rectangles. We can certainly put this rectangle around here. Again, this R is our choice and we have no idea what it is, but we only know it exists. But the 0 and beta is part of our setup. So there's not much of assumption, which is all facts we can accept. Next part is assumption. So this makes this entire proof a little bit weaker, but in part 2 we're gonna kind of take care of this limitation in here. First of all, we have this box, rectangular box D, and because f of xy, the usual hypothesis in differential equation, this is a continuous function of two variables. Therefore, by extreme value theorem, absolute value must attain a maximum on that rectangular box. So that maximum we're going to call M1. This M1 part and maximum part is not ineffective. We know what f of xy is, but we don't exactly know what the size of this R are. So therefore, this part on D part makes this M1 ineffective. We know the existence, but we don't know what this is. So here's the condition I was talking about. So I adjust a little bit, and this beta, which is part of the setup, here's a differential equation. This is where we start, and beta is something from 0 to, let's say, 3. Then we want to calculate the value in here, and so this is kind of our free choice, but here is some constraint on that beta. R was the radius with this about the solution function. M1 is the maximum that is involved in the differential equation there. And this beta, which we want to freely choose from 0 to whatever we want to estimate, has to be a little bit small. You can't go too far. You have to be bounded by this R. It's coming from a maximum minimum of the solution. M1, which is coming from the maximum minimum or maximum of the slope of a tangent line in there. If beta is not too big, so it's bounded by this one. If we're looking at betas quite close to 0, since it doesn't exceed this one, the following proof will be valid. In part 2 of the proof video, then we will use this result and put them together to go beyond this beta boundary. Alright, now this part is about the Euler method, and I'm showing you down there the setup of our problem. This h is increment of x values, which is calculated like this. We start from 0 to beta. So this length of this interval here is beta minus 0, divided into n pieces. N is usually a large number, let's say it was 100. That's what this h is. And xk is some intermediate value incremented by this amount. So x1 will be starting from 0, go k equals 1 h, so you go h more. So x3, for example, will be starting from 0, go 3 copies of h, so there will be 3h from that initial point 0. So this is the x values we uniformly distributed between 0 and beta, and h is the interval between those points. And this is how you calculate approximation, the Euler method points. We start from y0, and recursively we calculate next point using the previous point, zk, and this is exactly the linear approximation where we use derivative information from our differential equation. And we repeat this all the way up to k equals n minus 1, such that this value ends up at zn. So that's the sense of Euler method. And we want to see how this last value zn here is how close this one is to the last value y of beta there. So under that setup, we can prove two things. The first thing is this statement, which will not be proved here, but is usually assigned as a homework in my courses, so I'm just going to claim it here. And relative to the proof of this one, it's a lot easier, and it's just try to unfold this relationship between zk and y0 using this one here. It's relatively easy to conclude this one. But let me just explain what this means. So I put that picture up here again, hope it's not too confusing. I'm about to explain the meaning of the statement in here. It says that as we calculate all those Euler points, Euler method points from the Euler method, they're very close to y0. That's pretty much what it means. So here's y0, the distance from y0 to zk, which is y value in here. So I can project it onto this vertical line to compare it with y0. Suppose we're somewhere here on xk and zk was in here, and you compare that with the y0. That means distance from zk to y0 is less than or equal to r. And this is exactly distance r to above to below both r. So what this guarantees that the zk, one of the y-coordinates of the points coming from the Euler's method, is within this height. And xk, of course, is by our definition between 0 and beta. Therefore, this guarantees that our point xk zk, which is the points from the Euler method, is within that box, so it doesn't escape. So as long as this follows from the condition beta being less than and r divided by m1. So I put it up here right next to it. We had this weird condition so that we can't just look at wide solution. We have to look at very small neighborhood with this constraint. It's because we want this control. If we don't go too far, the Euler points, the points from the Euler method, is going to stay within this box so that we can have a control. You can use all the maximum and minimum value properties that we have a nice control. So this is very technical. Of course, this is probably far from the truth, but this is something we can guarantee for the sake of our proof, to make our proof work. In a part 2, and we are going to overcome this difficulty just patching these two individual results together to go further beyond this beta as small as this one. Alright, so let me explain again. This part here is not going to be proved, but it's going to be proved. This will use this property that beta being not too big, less than r divided by m1, and that's going to be usually the hallmark. So with that condition, our point is in this box. And the main point of this video is proving this result using that, knowing that our points from the Euler's method is within that box. With that much of a control, we can show the final points actually approaches our actual solution. It's interesting. This is we can conclude like this without even knowing what this y beta is.